A22 or Physics 5, Year 14, and it's Unit 1 Capacitors, and this was homework 2. So the first question, a capacitor is charged by connecting it to a source of variable potential difference. On figure 1.1, which is the first graph, and figure 1.2, sketch graphs to show the variation of potential difference of the charge Q on one plate of the capacitor and the energy stored in the second graph in the capacitor. So the first one, we need to find what's the relationship between Q and V. And the equation that we know is that Q is equal to CV. So we can tell from that that Q is directly proportional to V. And so that's going to be a nice straight line through the origin. The second part of the question asks you about the energy relationship between energy and voltage. Now we actually have two equations which connect those. We have a half CV squared and a half QV. But you decide which one you're going to plot by looking and seeing, is it capacitance that's constant or is it charge? And you can see it says in the question a capacitor, and so that capacitance isn't going to change. So this is the relationship here we want to look at when we want to plot it in the graph, and we can tell from that relationship that E is proportional to V squared, and therefore if you're going to plot a graph of E versus V, it's going to be an upward curve like that there, and that's your answer to your second graph. A capacitor is connected in series with a battery, a resistor and a switch. The capacitor is initially uncharged. When the switch is closed at time t equals 0, the capacitor begins to charge through the capacitance through the resistor. On figure 1.3, sketch a graph to show how the PDV between the capacitor plates varies with time. So obviously as the switch is closed, there's going to be a voltage. A voltage is going to build up on the capacitor plates, and it's going to be your usual charge-discharge graph, which is an exponential decay curve, and therefore it has to start at the axis and it goes down, and you can decide if it's just going to go very close to the t-axis or eventually it will hit the t-axis, but there's a reasonable amount of time will have passed in that case. This is page 2. Use the graph in figure 1.3 to deduce qualitatively how the change in current varies with time. On figure 1.4, sketch a graph of I versus T. So you know that V is proportional to I, and therefore if a graph of V versus T is an exponential decay curve, so is a graph of I versus T. Again, it should start at the axis and come very close to 0 on your T-axis. In this circuit, the resistor has a resistance of 10 kilo, that should be 10 kilo ohms, it says 10k, and the battery has a constant EMF of 20 volts. The time constant of this circuit is 0.5 seconds. Find the current at time t equals 0. So all you have to do then is, if you're looking for current, you're given resistance and you're given the battery voltage. So V is equal to IR. I is equal to V over R, and that's equal to 20 divided by 10. Now it's 10k, so watch out for that, and that's a very easy place to make a mistake. Be very, very careful about that, and that gives you a total of 2, and it's by 10 to the minus 3 or 2 milliamps. Next question, state an expression for the time constant of a circuit, and that's given by tau is equal to C times R, the product of capacitance and resistance. Show that the product of a resistance and capacitance has a unit of seconds using base units or otherwise. Now base units are quite difficult using for capacitance or resistance, so the easiest thing to do is just show it otherwise using the equations. So you know that tau is equal to C times R, and C is Q over V, and R is V over I. So you can see there that the V's cancel out and you're left with Q over I. So if we now write down units, Q is IT, which is amps times seconds, and I is amps, and you can see the amps cancel out, and you're left with the units of seconds. So the time constant tau is a length of time and its unit is seconds. The circuit below shows a capacitor of capacitance C. It's initially charged to a potential difference of V0. As you can see in this circuit, there's a resistor, a capacitor and a switch. And the capacitor is already charged to a potential difference of V0. So page 3. When the switch is closed, the PDV across the capacitor varies with time. If the initial current flowing in this circuit is I0, sketch a graph of I versus T for this circuit. Label this graph R. And so you have initial current and it's going to fall exponentially as usual. And so the initial current is I0 here. And it says label this graph R, and the reason is because we have a second graph to draw on top of it. What would be the effect if R was removed from the circuit? If R was removed, then it would discharge much more quickly. Charge or discharge much more quickly. So in this case it's discharging. And there's another effect as well. If you remove R, that means the initial current is going to be higher because you have less resistance in the circuit. So then whenever you are asked in the next question to sketch a second graph on the same axis, then you should use these 2 points you have on here. It discharges more quickly and therefore the curve is going to go down much more quickly, but also that the initial current is higher. So you start here maybe and go down much more quickly. And you have to label this one C. At a time equal to 1 time constant after the switch is closed, V is equal to X times V0, where X is a constant less than I. Complete table 2.1 giving the values of V at various times. So you know that at time t equals 0, V is equal to V0, but after time tau has passed, it has fallen to X times V0. Now you should remember from our calculations in your notes that once a time equal to the time constant has passed by, your voltage has now dropped to 37% or 0.37 of V0. And this is what we're going to write down beneath as well. But if you have another, if I just sketch this up here, so say you have got a time past there equivalent to tau. If you let another tau go past, so that's 2 tau, then it's going to have dropped to 37% of what it was here. So whatever its value was here, it's now gone down to another 37%. So it's 37% of 37%, or that would be equal to 0.37 by 0.37 or 0.37 squared. And so if we're calling this x in this question, that constant is this, then we're going down to x squared V0. And so on, then it goes to x cubed V0, x to the 4 V0. Name the mathematical function describing the variation of V with t. It's an exponential function. Obtain the numerical value of the constant x0, and we remember from our notes or from what the work I did up at the side there, that answer is 0.367 or 0.37 rounded up.